And also, next time when we get together, I'll show you two things. I'll show you the Catmull-Clark one, which is the one that most people use, and then I'll show you one that works on, I'll show you several that work on triangles. Right? Lots of times when you have these bad surfaces like this, you say, just take the pentagons and everything and make them triangles. Right? Just subdivide them into triangles. And then we'll have these triangle-based algorithms, and we'll let a triangle-based algorithm work on them. And the triangles, they help you a little bit. The pointer hell isn't so bad, okay? But it can still be quite challenging. Go ahead, I had a question.
So what's the advantage to having the quadratic Bezier curves as opposed to the biquadratic patches?
Well, they're both biquadratic.
All right.
Okay. Well, it turns out the biquadratic things over here are really biquadratic Bezier curves. Anything that's polynomial I can make into a Bezier. They're biquadratic Bezier patches. Okay? And the advantage of using Bezier patches is just they're easy to use. Okay? The nice thing about Bezier curves is in the cubic case we can specify 4 points, right, and we get this nice continuous thing. And we can get any curve, any cubic curve in the world by specifying 4 particular points. Right? For computer scientists, that's cool because we can't store continuous curves. Right? We have a discrete device. This way we can store 4 points and do it. In the case of a Bezier patch, we can store 16 points. Right? And we have this nice continuous thing underneath. And by moving these points around, we can get any bicubic thing out of it. Okay? And that's what's cool about these Bezier things is you only have to store these few points, right, in order to be able to do continuous mathematical things with them. And that doesn't happen very much in the real world. Okay? The question's here for a long time, and it was solved by this impossible to read paper in about 1998. The question here for a long time is what happens around the critical points? What really happens around the critical points? Is it nice and continuous? Is it, not continuous? What happens? And nobody knew for a long, long time until a guy from effectively Adobe wrote a paper, which still is, it took me only about 3 weeks to understand it. I mean, it's just almost impossible to understand. But it showed that actually things are pretty nice there. Right? That we really don't have to worry. And now, if things are pretty nice there, then all of a sudden you can take these things into the engineering world and start making vacuum cleaners and airplane wings and things like that out of them. And